Today we will talk about continuity. First, we discuss what it means for a function to be continuous at a point. Then we illustrate different ways in which continuity could be violated. After that, we return to discussion of continuity of basic functions. Finally, we state the intermediate value theorem and demonstrate its usefulness. In everyday language, the word continuous means having no breaks or interruptions. In calculus, continuity is used to describe functions whose graphs have no breaks. For instance, let's look at these two graphs of functions f of x and g of x. Which function, from your point of view, should be called continuous? If you answered the one on the left, you are correct. Function f, represented by a graph on the left, is continuous, and function g on the right is not. Specifically, function g is not continuous at a point x equals a. Now let's apply what we learned about limits to describe the difference between these two graphs. In the case of the continuous function f, the limit of f of x as x approaches a exists and equals to the value of the function at a. On the contrary, limit of g of x as x approaches a does not exist, because the right-hand limit is not equal to the left-hand limit. This suggests the following definition of continuity in terms of limits. A function f is continuous at a number a if the following three conditions hold. First, f of a is defined, that is, a is in the domain of f. Second, the limit of f of x as x approaches a exists. And third, the limit is equal to the value of the function at a. As an example, let's check whether the function f of x equals x squared minus 3 when x is less or equal than 1 and negative x plus 5 when x is greater than 1 is continuous at a point x equals 1. We need to verify the conditions from the definition. First, f is defined at x equals 1, and f of 1 equals 1 squared minus 3 equals negative 2. Now we need to check the existence of the limit. Since the function is piecewise defined, we compare the left and right-hand limits. Since for x less than 1, f of x is x squared minus 3, limit of f of x as x approaches 1 from the left equals limit of x squared minus 3 at 1 equals negative 2. Since for x greater than 1, f of x equals negative x plus 5, limit as x approaches 1 from the right of f of x equals limit of negative x plus 5 at 1 equals 4. We see that the left-hand limit is not equal to the right-hand limit. Thus, limit of f as x approaches 1 does not exist, and f is not continuous at x equals 1. When we graph the function, we see that the graph of f has a break, a sort of a jump when x equals 1. This confirms our conclusion that f is not continuous at 1. Generally, we say that f is discontinuous at a point A, or has a discontinuity at A if f is not continuous at A. A piecewise defined function is not necessarily discontinuous. Let's consider a slightly different function. F of x equals x squared minus 3 when x is less or equal than 1, and negative x minus 1 when x is greater than 1. Let's check for continuity at x equals 1. Again, f is defined at 1, and f of 1 equals negative 2. The limit of f as x approaches 1 from the right is the limit at 1 of x squared minus 3, which is negative 2. The limit of f as x approaches 1 from the left is the limit at 1 of negative x minus 1, which is also negative 2. Since both left and right limits exist and equal to negative 2, the limit of f of x at 1 equals negative 2. So the limit of f at 1 exists and equals exactly the function value. Therefore, f is continuous at 1. Our conclusion can be verified graphically. We see that the graph of f does not have any breaks at x equals 1. Let's compare the previous two examples side by side. The only difference is the location of the linear piece. In the first example, the equation of the line is negative x plus 5. In the second example, the equation is negative x minus 1. That means the line was shifted downwards by 6 units, so it connects to the parabola. In the next example, we will connect two polynomials by finding a suitable parameter. For what value of the constant c is f of x, which is cx squared plus 2x for x less than 2, and x cubed minus cx for x greater or equal than 2, continuous at x equals 2. We will check the requirements for continuity. First, f is defined at 2. Substituting x equals 2 into the second expression, we obtain 2 cubed minus c times 2. So f of 2 equals 8 minus 2c. Next, we compute left and right hand limits. limit as x approaches 2 from the left of f of x equals limit at 2 of cx squared plus 2x, which is 4c plus 4. Limit as x approaches 2 from the right of f of x equals limit at 2 of x cubed minus cx, which is 8 minus 2c. For the limit to exist, left and right hand limits must be equal. So we said 4c plus 4 equals 8 minus 2c, and solve for c. We obtain c equals 2/3. When c equals 2/3, limit at 2 of f of x exists. To compute the limit, we plug c equals 2/3 into one of the expressions for one-sided limits. Here I used the left-hand one. We get that the limit of f of x at 2 equals 4 times 2/3 plus 4 equals 20/3, which is the value of f at 2. Therefore, f is continuous at 2 for c equals 2/3. When the constant is 2/3, the graph of f of x consists of the parabola 2/3 x squared plus 2x over the interval -∞ 2 and the cubic function x cubed minus 2/3 x over the interval to infinity. As you see, the curves connect at point 2, 20/3, and the graph is continuous. Recall that f is continuous at x equals a if the following three conditions are satisfied. F of a is defined. Limit as x approaches a of f of x exists, and they are equal. If one of these conditions is violated, f has a discontinuity at a. There are three common types of discontinuities. Discontinuity at a is called removable if the limit at a exists but does not equal to the function value. This might happen if f is not defined at a, or when f is defined at a but is not the same as the limit. In this case, the graph of f has a hole at x equals a. Another type of discontinuity is a jump discontinuity, which occurs if the one-sided limits both exist but are not equal. Again, f may or may not be defined at a point a itself. Graphically, at a, the function jumps from one value to another. The piecewise defined function in the first example of this lecture had a jump discontinuity. Generally, jump discontinuities are common for piecewise defined functions. If one or both of the one-sided limits is infinite, we say that function has an infinite discontinuity. On the graph in this case, we see a vertical asymptote at x equals a. It is worth mentioning that these are not all possible discontinuities. For instance, sine of 1 over x has a discontinuity at 0, which is none of these three types. The reason is that sine of 1 over x oscillates infinitely often between 1 and negative 1 as x approaches 0. So neither the right nor the left limit exists or infinite. Now we will go over examples of different discontinuities. Consider f of x equals 2x squared minus 5x plus 2 over x minus 2. Since the denominator is 0 when x equals 2, f is undefined at 2, and therefore is discontinuous at 2. However, we can compute the limit of f of x as x approaches 2. The numerator can be factored as x minus 2 times 2x minus 1. Since in the limit we consider only values of x other than 2, we can cancel x minus 2 in the numerator and denominator and obtain limit at 2 of 2x minus 1, which is 3. Since the limit at 2 exists, function has a removable discontinuity at 2. You see that the graph of f has a hole at point 2, 3. This type of discontinuities is called removable because we could remove this discontinuity by redefining function f at just the single number 2. If we define f at 2 to be 3, the function becomes continuous. Next is an example of a jump discontinuity. Consider f of x equals 4 if x is less than 2 and 2x minus 5 if x is greater or equal than 2 at a point x equals 2. Since for x less than 2, f of x is a constant 4, the left-hand limit of f at 2 is 4. The right-hand limit of f at 2 is the limit of 2x minus 5 at 2, which is negative 1. Since both one-sided limits exist but are not equal, we conclude that f has a jump discontinuity at 2. The graph of f is a horizontal line y equals 4 to the left of 2 and line y equals 2x minus 5 to the right of 2. Notice that the graph jumps down from the value of the left-hand limit 4 to the value of the right-hand limit negative 1. The size of the jump is the difference between these two limits. Unlike the removable case, we cannot make f of x continuous by redefining it at just one point. We would have to redefine f on a whole interval to connect the two pieces of the graph. Also, f of 2 equals -1, which coincides with the right-hand limit of f. To describe this behavior, it is convenient to define one-sided continuity. A function f of x is called left continuous at x equals a if the limit of f of x when x approaches a from the left equals f of a, and is called right continuous at x equals a if the limit of f of x when x approaches a from the right equals f of a. In this example, f is right continuous at 2, but not left continuous. The last is an example of infinite discontinuity. Consider function f of x equals -x squared plus 2x plus 1 if x is less or equal than 2, and 1 over x minus 2 if x is greater than 2, at the point x equals 2. We see that f is defined at x equals 2. Substituting 2 for x into the quadratic polynomial, we get -2 squared plus 2 times 2 plus 1 equals 1. The left-hand limit of f at 2 is the limit of -x squared plus 2x plus 1 as x approaches 2 from the left, which is 1. Since the left-hand limit coincides with the value of the function, f is left continuous at 2. The right-hand limit of f of x at 2 is the limit of 1 over x minus 2 as x approaches 2 from the right. Since x only takes on values which are greater than 2, the denominator x minus 2 is positive. Therefore, the limit is positive infinity. Because the right-hand limit is infinite, we conclude that f has infinite discontinuity at x equals 2. The graph of f consists of a parabola -x squared plus 2x plus 1 on the interval -∞ 2, and a shifted hyperbola 1 over x minus 2 on the interval to infinity. We see that f increases without bounds as x approaches 2 from the right. On the other hand, f is continuous from the left at 2. After looking at some examples of discontinuities, we focus again on continuous functions. We say that a function f is continuous on an interval if it is continuous at every number in the interval. We understand continuous at the end point to mean continuous from the right or continuous from the left. To bypass checking the three conditions of continuity explicitly, we invoke a general theorem. The following types of functions are continuous on their domains: polynomials, rational functions, root functions, and trigonometric functions. These facts are quite intuitive because the graphs of these functions do not have any visible breaks on their domains. However, the formal proof of this theorem would be a rather lengthy digression, which we omit. We can build more continuous functions by taking sums, products, and quotients of the above listed ones. The next four laws of continuity follow directly from limit laws. If f of x and g of x are continuous at x equals a, then the following functions are also continuous at a. The sum f of x plus g of x and difference f of x minus g of x. K times f of x for any constant k. The product f of x times g of x and the quotient f of x divided by g of x, provided that g of a is not 0. We also have a statement about continuity of composite functions. If a function g is continuous at a and function f is continuous at g of a, then the composite function f of g is continuous at a. The next four examples illustrate how these results are applied. In each example, we determine where the function f is continuous. The first function, f of x, equals 15x to the 58th minus 71x to the 11th plus 5. This function is a polynomial, and therefore it is continuous on the real line. The second function, f of x, equals square root of x minus x cubed minus 4x plus 7 divided by x squared minus 1. This function is a difference of a root and the rational functions, so it is continuous on its domain. Let's find the domain of f of x. The expression under the radical has to be non-negative, so x has to be greater or equal than 0. Also, the denominator of the rational function cannot be 0, so x cannot be plus or minus 1. Rewriting the domain of this function in interval notation, we get the intervals where f of x is continuous. F is continuous on 0, 1 and 1 infinity. Here at 0, f is continuous from the right. The third function, f of x, equals sine of the square root of 7 minus x squared. F is a composition of three different functions. F is a composition of a trigonometric, root, and a polynomial functions. So again, it is continuous on its domain. To find the domain of f, we set the expression under the radical to be non-negative. So 7 minus x squared has to be greater or equal than 0. Solving this inequality, we obtain that f is continuous on the interval negative radical 7, radical 7. At the endpoints of this interval, we have one-sided continuity. The fourth function is piecewise defined. F of x equals x squared minus 8 if x is less or equal than 3, and 1 over x minus 2 if x is greater than 3. For x less than 3, f is continuous as a polynomial. For x greater than 3, f is continuous as a rational function whose denominator is not 0. So the question is, what happens at 3? F of 3 equals 3 squared minus 8 equals 1. The left-hand limit of f at 3 equals the limit as x approaches 3 from the left of x squared minus 8 equals 1. The right-hand limit of f at 3 equals limit when x approaches 3 from the right of 1 over x minus 2, which is again 1. So the left-hand limit equals the right-hand limit equals the value of f at 3. This means that f is continuous at x equals 3. Function f does not have any discontinuities, so it is continuous on the real line. One key property of continuous functions is that they satisfy the intermediate value theorem. Suppose that f is continuous on the closed interval ab, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval ab such that f of c equals n. Let's visualize how this theorem works. Let f be a continuous function on the interval ab, and n be any intermediate value between f of a and f of b. Let's draw a horizontal line y equals m. Suppose we started at point A, f of A. As x increases from A to B, we move along the graph of the function and eventually end up at point B, f of B. No matter how twisted the graph of f of x might be, it has no gaps, and therefore must cross the horizontal line somewhere. We denote the x-coordinate of the intersection point by c. Then f of c equals n. One use of the intermediate value theorem is that it guarantees the existence of roots of equations even when they cannot be solved algebraically. In this example, we will use the intermediate value theorem to show that there is a root of the equation x equals cosine x in the interval 0, 2. Consider function f of x equals x minus cosine x. F of x is continuous on the closed interval 0, 2 as a difference of a trigonometric function and a polynomial. Actually, this function is continuous on the real line. The value of f at 0 is 0 minus cosine 0 is negative 1 because cosine 0 is 1. F of 2 equals 2 minus cosine 2, which is positive, since cosine cannot be greater than 1. Therefore, 0 is between f of 0 and f of 2. We apply the intermediate value theorem with a equals 0, b equals 2, and n equals 0. Then, the intermediate value theorem guarantees that there is a number c in the interval 0, 2 such that f of c equals 0. In other words, there is a number c between 0 and 2 such that c minus cosine c equals 0. So c is the root of the equation x equals cosine x. This is the end of our lecture.